We'll do a lot more on energy for test 3, but for now, specific heat capacity we'll go over today. Enthalpy, this says enthalpy, heat from reactions. It can also be heat that goes into reactions. And we use this symbol to represent enthalpy. It's just a fancy word for heat. That you mix two things, a reaction happens, heat comes out. We call that amount of heat enthalpy, or enthalpy of reaction. Sometimes heat goes in, but I'll get to that in a minute. And I've got some extra practice for these, because there's only a few of these at the end of the chapter in a PowerPoint that I've uploaded. But let me show you what heat capacity is. First, I've got table 9.2 listed here. If you go to table 9.2, I've added it to this PowerPoint. It looks like this. Notice for heat capacity, we use a capital C. They put an S here. I'm used to seeing a P there. And the units are joules per gram per degree C. That's the units for, I should say, specific heat. This is frequently just called specific heat. But this is how it works. It's not too complicated. I've got the values from table 9.2 written down here. I will give you these on a test. You'll need to answer these types of questions. But let me just go here. I've got those questions written down too. I don't know why the camera's so dim. Okay, so here's a question. 2.50 kilograms of sand is heated from 25.0 degrees C to 100.0 degrees C. How much heat does this take? And that's going to be in joules, which we represent with a J. The one thing you need here is the specific heat capacity of sand, which is in that table. I've got it written down here, so I don't have to keep looking at that table. But I'll give you that table in the test. Sand. Heat capacity for sand equals 0.84, and that's joules per gram per degree C. As I frequently tell you, go ahead and think of this as 0.84 joules, that's my capital J, per 1 gram to 1 degree C. So if you have that at hand, you can use this information to solve for this problem. Also notice there are two things here. There's what we call temperature initial and temperature final. And usually in context, it'll say from this degrees up to this degrees. So it starts here, that's T initial, and that's T final. And you're going to need what we call delta T, which is always final minus initial. That delta T is really what goes here for the 1 degree C. So in this case, 25 is initial. That's initial, and final is 100. So if you do this math, delta T equals 100 minus 25 to 75.0 degrees C. So what we call that is delta T equals 75 degrees C. Just when you think this is going to get more complicated, to solve for joules, all you have to do is specific heat capacity per gram per degree C, and then we're going to put 2.50 grams. This, and then the delta T, you stick the delta T in for degree C. 75.0 degrees C equals, so now the grams will cancel, degrees C will cancel, and you'll end up in joules, which is what you want. How much heat does this take? So it's just 0.84 times 2.50 times 75. .84 times 2.50 times 75 joules. I guess I have to stick to two significant figures because of this. 7 rounds to 5, so 160 joules. It takes 160 joules of energy to heat 2.50 grams of sand 75 degrees. You follow that? I think it's the temperature initial and final and the delta T as little extras that make this seem complicated. Other variations on this type of problem, I will do, that was question 42. That was this one. Other variations you'll get is, I'll do one from 43. Okay, which ones do y'all are y'all given? So you're given 43. I'll still do one from 43. 43. This one just changes the problem a little bit by saying I have 25 grams of the substance. The initial temperature is this, and it's asking for the final temperature. 2.35 kilojoules. Is the heat. Since this is in joules, I'm going to need to turn the kilojoules into joules. Yeah, 235 kilojoules. So I just convert it to joules by moving the decimal 3 times to the right, and that just simplifies everything. If you want to solve for this, it is 235 joules equals, and we've got the substances. Okay, so for the first one, the substance is gold. And if you look on the table, gold is 0.128 joules or 1 gram or 1 degree C. So you need that. Joules, and we're solving for, well, should I write it out this way? Let me write it this way. That's this flipped over. Need to end on temperature final. Oh, I should have worked this out before class. And then 25 grams, so we're going to put the 25 grams on top. And then my delta T is, delta T equals temperature final is temperature initial. So that's what I'm putting in for my delta T. So my delta T will go here. That's going to end in joules. So there's 4 of these. It does gold, silver, aluminum, and water. Here, if you solve for T final, you get the answer. Everything counts. But, yeah, that's the way I would say it. Okay. Joules are going to cancel. Degree C is going to cancel from here. How would I do this? Divide both sides by 0.128 and divide both sides by 25. Units. Joules cancel, grams should cancel. That will work. I've just done something weird with the units here. That will give you temperature final. This works as a setup. If you set it up like this, the only problem with that is all the algebra to get to TF. But this is doing all the algebra. That minus that plus. So there are 4 of these: gold, silver, aluminum, another one. They're all done the same way. This, I think, is the best conceptual way to set it up. I think that works algebra-wise. Divide both sides by 0.128, then divide by 25, and then add 27.0. But I have been sloppy for the units. 2350 divided by 0.128 divided by 25 plus 7. I bet I'll get the answer. 2350 divided by 0.128 divided by 25. No, mine's off a little bit. Oh no. Plus 27. Oh, I'm right. What I get from that for T final? 761.375 degree C. But we're stuck with two significant figures, so it's those. So it's 760 without the decimal. The answer in there says that's the same as 760. I did get sloppy with the units. This is the best conceptual way to think of those for 43. This is with the algebra simplified, however you want to remember it.
I'm just confused at how you're taking like the problem and then like setting it up into an equation. How?
This is given in the problem. These are given in the problem. And this is given in the problem. This is the heat capacity that I looked up on the chart. So I've got that plugged in there. I've got the grams on top. And you have to infer that final minus initial, final minus initial, final minus initial. The initial is 27 degrees C. And then it says it takes 2,350 joules to do this process, and then you're just solving for temperature final. And every one of these will be set up that same way.
Okay, so you just have grams and temperature on the top to cancel out the 1 gram, 1 Celsius.
Yeah, once you do this math, you have degrees C and you have grams there. So this is what screwed. I didn't follow the units through, but that's going to cancel and that's going to cancel. And you have joules to joules. But once you rearrange it this way, you'll end up in degree C here. Was the algebra too much?
I was slowly figuring out how you.
Did you write it down?
Yeah, we can.
Just write it down.
Thank you.
And I think 44 is the same as these. But you don't get the answers to. This time they're giving you the temperature final in 44. And initial versus much heat. Okay, so now we're finding the mass for 44. 43. Times grams. If I gave you a general way to solve 43, I would just say that. You're given this in the chart, you're given this, you're given this, and you're given this. Here's the things you're given in 43. You're given a number of grams, you're given a temperature initial. These are just ones. This comes from the chart, so you get that too from the chart, and you're also given this. and you're solving for temperature final. With a bit of algebra, you can get here, but that's being sloppy with units, but you do end up in degree C there.
Was it a same like they put at the bottom how you cancel out the units?
Sorry.
Like how you cancel out the units at the bottom. That's what I'm confused.
That's what I'm saying. I was sloppy with the units getting here. I can return to that, but if you just set it up this way and you just solve for temperature final, it'll work. Any questions? Okay, let me show you how 44 works. Very similar, except this time for 44. I'm going to leave that there. For 44. Here for 43, you find temperature final. You're solving for that. For 44, you're finding mass. So this one is set up by asking. The substance is Pyrex, so you look that up. It tells you, here's what you're given. Temperature initial is 23.0 degrees C. Temperature final is 55.4 degrees C. So you're given those things. And you're also given the joules. But they give you 1.95 times 10 to the 3. And you can go ahead and turn that into 1950 joules. So you're given the temperatures this time. You're given the joules. And you're also going to need the specific heat capacity for Pyrex, which is in that chart. Chart 9.2. One over there. So there's Pyrex, 0.75. So Pyrex is 0.75 joules to 1 gram to 1 degree C. So that's what you're given, and now you're solving for mass. So you could set it up the same way, except now you're given this and not this. So I will go. So the joules I've got is 1950, which is specific heat capacity is 0.75 joules to 1 gram. 1 degree C. Next, I'm solving for the mass, so I'll just put an X there, X grams, and final minus initial. Final minus 23.0 degrees C, and solve for X. So it's set up the same way. The algebra will be a little different by the end. So let's see if I was solving this. The simple way is 19.50 joules divided by joules. Divided by 0.75, and then divided by by 0.75, divide by this, that'll give me X grams. Yeah, that's right. Divided by 0.75. I better do the subtraction first. 55.4 minus 23.0. So this ends up being 32.4 degrees. 32.4 degrees C. Now I can do that. 1950 divided by 0.75 divided by 32.4. So I'm getting X equals 8 grams. Because of two significant figures, I'm stopping here. It was 80.2 something, something, something. 8 grams. We can go back over this. I know I'm not quite with it today. But again, it's set up the same way that is. You're just given different variables this time. You're given both the temperatures. You look up this on the chart. You're given the joules that evolve from this. You can solve for grams. I made that seem a lot more complicated than I think it is in my own head. So there's those, and this other thing I'm sure is more simple, even though enthalpy sounds more complicated. Let me go to, I'm going to write these down. No, I'm going to write these down. These exercise 56, 57, and 58. Let me use an example out of the book here. Push that aside, given that I made it seem way complicated, and focus on enthalpy, because I promise this is a little more straightforward. I'm going to write this reaction. So this should look more familiar. I'm going to write out a reaction. So there's a reaction. And then out to the right here, I'm going to put delta H reaction. 0.044 kilojoules. So this doesn't involve a specific heat capacity, but it's very similar to the things we've done before. So you know what this means. You put these two things together, they react and become this. In the process of that happening, this much energy leaves the reaction. It has a negative because it's leaving the reaction. Like if you had this in some kind of chamber and you had a reaction go, this much heat would come out. You would feel heat come out. This is combustion, so you're familiar with things burning and giving off heat. The negative is telling you, with respect to these molecules, heat comes out of them, this much heat comes out of them in the process of that reaction. That's why there's a negative sign. It is possible to do a reaction that absorbs heat, and then this would be positive. But when it's negative, you say it's exothermic. So I'll write this up here. Delta H negative because heat is leaving. Sometimes delta H is positive. Let me say it absorbs heat from the surroundings. So you can get it to happen either way. This one happens to be exothermic, and you can tell that because this is negative. It's telling you this much energy left the reaction. If it was positive, it'd tell you how much energy the reaction absorbed in the process. You with me so far? Exothermic, endothermic. You can tell that literally just by looking here at this sign. This tells you energy came out when this reaction happened. If it was positive, it'll tell you energy went in during the reaction. All right, endothermic, exothermic, and then the rest of this is just.
So is that going to be like a question on the exam?
I could ask you that. And you're literally just looking at that sign.
Okay, gotcha.
You might do a calculation and then answer it. But let me go down to where there's an actual question. So they're using that same reaction here. And what they're saying is, they do tell you that C3H8 is propane. I'm just going to call it C3H8. And they're saying 13.2 kilograms of this reacted. So how much heat came out? You might think, well, you just told me this is much heat came out. Well, this is saying if 1 mole of propane reacted, that's how much heat would come out. But we need to see how many moles this is, this kilograms. Now, of course, you're going to do this. Let's see if they calculated it for me. They did somewhere. I'm just going to use it. The molar mass of C3H8 is 44.09 grams per mole. 44.09 grams per mole. So this is 44.09 grams per mole. So we've worked with grams per mole before. And I always tell you to think grams per mole of C3H8. C3H8. So you recognize this, right? Something we've worked with before. Just like before when I set this up, I told you there's a molar ratio of this to this. It's 1 to 5, 1 to 3, 1 to 4, 5 to 3, 5 to 4, 3 to 4. Those molar ratios. In the same way, there's 4 relationships here related to energy, and they're this. 1 mole of C3H8. I think this works out better, usually, if you write the relationship this way. 1 mole of C3H8, negative 2044. There's one of the relationships. Another relationship, 2044 kilojoules to 5 moles of O2. So that's that relationship. For this one, negative 2044 kilojoules to 3 moles of CO2. And then one more, the 4 moles of H2O. Those are the 4 relationships that are summarized in this reaction when we have the enthalpy added there. And this question is asking about propane. So it's this one I'm going to be using. I'm going to use this and this 13.2 kilograms. I'll start with kilograms. Since this is in grams per mole, I have to convert from kilograms to grams. 1,000 grams is 1 kilogram. Now I'm going to go 1. I should have, let me be formal here. C3H8. And then 1 kilogram of C3H8 is 1,000 grams of C3H8. Parentheses. And now I'm using this 44.09. The C3H8 is 1. C3H8. And I'm almost there. Now I need this 1 mole of C3H8. Negative 20, 44 kilojoules. And then we'll end on kilojoules, and that's fine. All right, 13.2 times 1,000 times, you don't have to do the negative here. So I'm just doing 2044. Divided by 44.09. The answer I get is 611,948,28759. Exact. 4 significant figures, 4, 3. So I guess I'm keeping these. So 612000, no decimal. Kilojoules. This is the example in the book, in the chapter. Let's see. Right there. 6.12. They've got 6.12 times 10 to the 5. That's the same thing I have there. This is example 9.7. So all of these are just like that. Let me double check. So even if you hated the heat capacity thing that I made seem complicated, it really isn't. At least follow the enthalpy thing here. 56, 57. What mass of natural gas is CH4? Oh yeah, that one is slightly different. So let me do that one. Okay, 57 is like the one I just did. It's asking for the heat. 48 and 56 are asking for a mass. So let me do example 56.
Oh, Dr. Hungry. The 44.09, was that just the formula mass of C3H?
44.09? Yeah. I mean, if I did C, there's 3 of them, H, there's 8 of them, times 12.01, times 1.01, and I added them up, it would be 44.09. Just the formula mass. Okay, so one variation on this asks you for the energy that comes out given a certain amount of mass of one of these. The other type of question is you're given the energy and you find the mass that's reacting. I'll do 56. That was example 9.7. Now I'm going to do number 56 at the end of the chapter. So there will always be a reaction to look at. CH4 plus 2O2 reacts to make CO2 plus 2H2O. So I did 9.7 in the chapter, and I'll put over here delta H equals negative 8.3 kilojoules. So there's your information. And it asks you for what mass of CH4. You're going to need the grams per mole. 12.01 plus 4.04, so 16.05 grams per mole for CH4. 12.01. So this is so we're going to need that for CH4. We're also going to need this relationship, negative 802.3 kilojoules to 1 mole CH4. So we're going to need that as well. To find grams, I think that's all we need. Grams, mole.
Is it 802.3 or is it 802.3?
802.3. Something's missing. Oh. So this is missing. That's how much. So it produces this much heat. That is, this much heat comes out of it when there's 1 mole of CH4. It's also true when there's 2 moles of O2, everything will be the same and it'll still be this. But it's saying mass. The mass isn't necessarily 1 mole, so we need this to help us. So I start with 3, 2, 5 kilojoules, and then I want kilojoules on the bottom, so I'm going to use this flipped over. Kilojoules to 1. And now I'm going to use this, moles on the bottom. That'll end on grams. Let's see. I get 325 times 16.05 divided by 802.3. 6.5 grams. Exact. 4 significant figures, 3. So it stopped at 3. What else to say there? I guess that's the answer to this one. So you're either given this and asked for mass, or you're given the mass and you're asked for how much heat is produced. Again, this is just a standard heat when there happens to be exactly 1 mole. The variation is you're not always necessarily dealing with 1 mole. What about this? What if it asked for the mass of O2? I want one that has an actual number there instead of 1. 1 mole to CH4 because there's a 1 here. But if I was doing oxygen, it's O2 and oxygen is 16.01, so 32.02 grams per mole. Grams per mole for oxygen. So I'll need that. And the relationship for oxygen is 2 moles to 802.3. And then I would put here, so if I were solving this for oxygen, I would use the same 325 kilojoules, but now I'm using this molar relationship for oxygen, and then the grams per mole for oxygen, and I would solve it for oxygen. I just wanted to do one that had something other than 1 here to emphasize that this comes from here, because all the examples I've done so far happen to just have 1. Okay, and I'll go over heat capacity again when we review. So don't agonize over it or make it seem harder than it is. This is from another class. I figured we'd lean on it. So there's the reaction. There's the delta H. I guess I should say this number from that text that I was using, they're saying that's the enthalpy change. This is the standard enthalpy change when there's 1 mole of this and 2 moles of this, 1 mole of this, 2 moles of this. If there's something other than those moles, it's still an enthalpy change. It's just an enthalpy change for whatever mass is used. Enthalpy change. Okay.
Doctor,
Yeah.
how come the answer wouldn't be negative since the temperature is negative? I mean, not temperature, but -8 and -2.
What does the negative mean? That I keep leaving it
No,
off?
just when I put it in my calculator, it gave me a negative answer.
Okay. Tell me what your calculators, did you do this one?
It got to 6.5 when we were doing it for CH4, but it gave me a negative 6.5.
You just use the absolute value for this.
Okay.
It does mean something when we calculate the energy, but I'll emphasize that when we do test 3. It's really not complicated, but it seems complicated. Since I seem to make things seem complicated today, I won't go into it. So just use the absolute value when it's negative, and everything should work out. I'm going to stop there because that's where test 2 is going to be. I'll tell you what lab we're doing Friday, but you don't have to do any pre-lab for it. Just bring your notebook like we usually do. Fill it in as we go. This.
It's just basically like these.
On
Have a good rest of your day.
You too.